Hi everyone, this is Maverick Paul, the Chemistry Guru. Now in this video, we want to discuss the suggested solution for 2021 A-Levels H2 Chemistry, Paper 1, Question 18. Now question 18, 2-bromopropane undergoes nucleophilic substitution at a faster rate than 2-chloropropane under the same conditions. Which two statements explain this? We have four statements to consider. Statement number 1, the ionization energy of bromine is less than the ionization energy of chlorine. Statement 2, the shared pair of electrons in the carbon-halogen bond is more shielded from the halogen nucleus in 2-bromopropane than in 2-chloropropane. Statement 3, the atomic radius of bromine is larger than the atomic radius of chlorine. And finally, statement 4, there are more protons in the nucleus of a bromine atom than in the nucleus of a chlorine atom. And we're given four options A, B, C, D, so we will have to decide which is the best answer. Now, the topic tested in this question is under halogenoalkane, targeting nucleophilic substitution, and the reaction is written here. Basically, 2-bromopropane or 2-chloropropane. I just write down the bromine and the chlorine as halogen X to generalize it. So basically what happens is the halogen on position 2 undergoes substitution. I'm using hydroxide as an example to give me our alcohol. So we just want to write down this reaction in general, then we have a better idea what the process involves and see involving which of these statements, whether they are relevant or not relevant. So let's run through each of these statements part by part. Now statement 1. Statement 1 says that the ionization energy of bromine is less than that of your chlorine. Now, if I consider ionization energy, which is the energy required for me to remove electron from bromine atom or your chlorine atom. So again, if I just write it in terms of X, which is halogen in general, ionization energy will be involving our halogen atom. Take out one electron to give me X plus in the gaseous state, plus 1 mole of electron. Basically, removing 1 mole of electron from 1 mole of your gaseous atoms to form 1 mole of gaseous cations with a +1 charge. Now, if you think about this, regardless of whether ionization energy of bromine is less than or greater than ionization energy of chlorine or not, regardless of whether this is true or not, it doesn't really matter. It is not relevant because if I consider the process is involving my OH minus coming in and kicking out your X minus, so this nucleophilic substitution doesn't involve our halogen losing its electron to form X plus. Therefore, statement number 1 is not relevant. Number 1 definitely is incorrect. Now next, let us look at statement 2. Now statement 2 is interesting because it is phrased in quite an unusual way. So we might not know what it represents, but let's try to break it down and try to understand this in detail. Now the shared pair of electrons in the carbon-halogen bond is just basically the 2 electrons between the carbon and your halogen, or usually we just call this the bond pair of electrons. And this bond pair of electrons between your carbon and your halogen is more shielded from the halogen nucleus in your bromo compound than in your chloro compound. Now what affects the strength of a covalent bond? Now a covalent bond is defined as the electrostatic attraction between the bond pair of electrons and the 2 nuclei that is sharing this bond pair of electrons. So essentially it is just the overall attraction between your nuclei attracting this bond pair of electrons plus the other nuclei also attracting the same bond pair of electrons. So basically the overall attraction will be my covalent bond. Now what I'm using here is a simpler model using Bohr's model, talking about the number of principal quantum shells, because I think it is easier for us to visualize the number of inner shells that can shield the valence electron or the bond pair of electrons. So we know that carbon, it is in period 2, so you have 2 shells. Chlorine is in period 3 with 3 shells. Bromine is in period 4 with 4 shells. And let us take a look at the arrangement involving your carbon-chlorine bond versus your carbon-bromine bond. Now, carbon-chlorine bond, the arrangement is something like this. Now, if I take a look at your chlorine, the question is focusing on the shielding involving chloropropane versus bromopropane, the shielding from your halogen nucleus. And if I consider your chloro compound, there's one inner shell which is represented in blue, another inner shell which is n equals to 2, represented by this green ring here, and the valence shell is in n equals to 3. So this means that for your chlorine, we actually have two inner shells acting as a shield to block the attraction between the nucleus and this bond pair of electrons. So it actually affects, or it reduces, the overall attraction between the nucleus and this bond pair of electrons, and it will actually affect the strength of your covalent bond, or it will affect the bond energy. So if I compare this with bromine, now bromine actually, since it is in pure form, and therefore you have three inner shells. The first inner shell, which is represented in blue, second inner shell, which is represented in green, third inner shell, which is represented in orange, then followed by the valence shell, which is n equals to 4. And you notice for this bond pair of electrons, between this bond pair of electrons and your bromine, there are actually three inner shells. There are more inner shells, which means that I will have one more additional inner shell to exert a greater shielding effect. There will be a weaker attraction on your bond pair of electrons. You cause this carbon-bromine bond to be weaker, and it means that if it is weaker, less energy is required for me to break this bond. It causes it to be more reactive. So if I compare your CCr bond versus CBr bond, involving chlorine, I'll have less inner shell, less shielding. Attraction between the chlorine and the bond pair will be stronger. This means that your CCr bond will be stronger. More energy required for me to break this bond, it will be less reactive. Involving CBr bond, because bromine has more inner shells, shielding effect will be greater. Weaker attraction on a bond pair of electrons. This means that your CBr bond will be weaker, and therefore this is more reactive. And if I come back to the second statement says that the shared pair of electrons, or the bond pair of electrons, is more shielded from the halogen nucleus in 2-bromopropane. Actually, this statement is true. It causes the bromo compound to be more reactive, which is consistent with what the question is saying. So statement 2 is correct. It will be part of the answer. Now next, how about statement 3? Now statement 3 says that the atomic radius of bromine is larger than the atomic radius of chlorine. Now actually, usually we will use this to explain why your bromo compound is more reactive than chloro compound. You can just simply say that because the bromine, it is bigger in terms of size, and therefore the CBr bond will be longer and weaker. The longer the bond, the weaker this will be, and therefore the bond energy is lower. Less energy is required for me to break this bond. Turns out to be more reactive. So this is actually the default explanation that we will use to talk about the reactivity for halogenoalkane. As you go down the group involving halogens, we will expect your aldo compounds to be the most reactive, followed by bromo compound, followed by chloro compound, and fluoroalkanes, actually they are not very reactive. The CF bond is actually very stable because the bond is shorter and stronger. So statement number 3 is correct. Number 3 will be part of the answer. Now finally, involving statement number 4, there are more protons in the nucleus of a bromine atom than in the nucleus of a chlorine atom. Now, the number of protons actually affect the nuclear charge, and in bromine, which is true that it has more protons, this means that the bromine will have a greater nuclear charge, and a greater nuclear charge will be able to attract the bond pair of electrons more strongly. Again, if we refer back to the diagram, what we have here is, remember the strength of your CBr bond, it depends on the attraction between the nucleus and the bond pair of electrons. And therefore, if I have more protons, the nuclear charge will be greater. Nuclear charge is greater, you should be able to attract this bond pair of electrons more strongly. And the consequence involving that is it should cause the CBr bond to be stronger, and it should turn out that it is less reactive. But the question tells us that our bromo compound is actually more reactive, so this actually doesn't explain why bromopropane is more reactive. In fact, it is trying to explain why bromopropane is less reactive. Therefore, statement number 4 is also not true because it doesn't give us the correct outcome. So now we can run through the options. We already have run through all the 4 statements. Statement number 1 is not true. Statement number 2 is true. Number 3 is also correct. Number 4 is not correct. And therefore, the answer to this question will be option B. Statement number 2 and number 3 will explain this observation. Alright, so that was the discussion involving this question. Now, if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.